The second video for chapter 13 on states of matter is going to be all about liquids. So we're going to be focusing on liquids for the next two videos. So we have already looked at this a little bit before. We've talked about, this table right here, table 11.2. What is a liquid? A liquid is where the energies of the particles, so the kinetic energy of the particles is about-ish equal to the energies of attraction between the particles. So as you can see over here, the particles are able to move past one another, but not able to completely break away, right? If they have enough energy to completely break away, then it would be a gas. But they don't, so they can move past each other, but they are not completely free from those attractive forces. This picture right here shows sort of the same thing, right? And read the text down here. Solids are rigid because their particles can't overcome the attractive forces locking them in place, right? These particles have so little energy because they're at a low temp, they're not able to overcome any forces holding them in place. Liquid, right? They can move more freely, so they can slosh about and they need a container, but they can't completely break free. That's when you have a gas. When they can completely overcome attractive van der Waals forces, we can call them intermolecular forces in a moment. Okay, they need a container with a lid. So being specific, or in order to be specific here, what keeps the particles in place? Well, in an ionic compound in metal, it's bonds, right? It would be ionic bonds, right? The positive and negative attraction between cations and anions, or metallic bonds. And remember, metallic bonds is that electron C. And we know bonds are very strong. It takes a lot of energy to break them. In covalent compounds, covalent bonds are still very strong. But, and this is the big deal here, when a covalent compound goes from being a solid to a liquid to a gas, you do not break the covalent bonds. That's why it's different. It's intermolecular forces here. And I will always say, you guys already know this. You know that water vapor is water vapor. It's one oxygen and two hydrogen. The oxygen-hydrogen covalent bond does not break up, right? This is looking at another model. And these would all be at the same temperature. So at the same temperature, compounds with the least intermolecular forces. We know least intermolecular forces can be, we will review these again, but those could be London dispersion forces. Those could be a gas. What is the most intermolecular force, or the strongest intermolecular force? We know that that's hydrogen bonding, right? But there are, which is really, remember, this was a big deal. Hydrogen bonding is a bad name for the strongest intermolecular force. So we're just going to review these because, as you can see, with covalent compounds, it's all about the intermolecular forces. So the weakest intermolecular force that there is are London dispersion forces. This was the temporary dipole, or induced, and then it induces a dipole. So the temporary dipole that is formed by any molecule. So this is in any molecule. Actually, any molecule or atom, if you're talking about something like neon, a noble gas. Any molecule or ion, just when the electrons are not evenly distributed. Right? For a split second, the electrons, like let's say this is a helium atom. So here are its two protons, and then for a split second, its two electrons are on one side. You know, they're constantly moving and orbiting the nucleus. And if that gets near another helium atom, you can get opposites attract. You can get an attraction going on between the two. Here is another view of London dispersion forces, right? So this is basically the same thing that I just talked about, where you have the positive nucleus in the middle, the electrons are orbiting around. If the electrons get on one side of the atom, this side of the atom will be partially negative. This side of the atom will be partially positive. If this is the partially negative side, it will push the electrons like charges repel, and you will have the electrons over here, and you will have positive and negative attraction. So this is in every single molecule or atom has London dispersion forces, but where it is important is nonpolar molecules and atoms, because those are the only intermolecular forces that nonpolar molecules and atoms have. If you have a polar molecule, you could have the medium strength, the dipole-dipole forces, or the very strong hydrogen bonding, or the hydrogen bonding force. The dipole-dipole forces are between all polar molecules, right? We only have a few forces in all of science. This is one of them, the electrostatic force, opposites attract. Hydrogen bonding is just a stronger version of dipole-dipole. It's whenever hydrogen is bonded to the three most electronegative elements: fluorine, nitrogen, and oxygen. Not only are they very electronegative, but they're also very small, and that's a big piece of it, that they are actually fairly small, and that makes this attraction quite strong. So medium dipole-dipole forces, they're between all polar molecules. Remember, what is a polar molecule? Is where the electron density is not evenly distributed. And if you're still like, I don't really remember that, look back at chapter 8. That's where we went through a lot of this. That's where we figured out a lot of this. Okay, so we have this sort of London dispersion forces, weak, dipole-dipole forces, medium, hydrogen bonding, strong, but it isn't quite that easy. Typically, the stronger intermolecular force, the higher the melting and boiling point, because more energy is needed to overcome the intermolecular force. That's the big deal here. If you have a really molecule with very strong intermolecular forces, it's going to boil at a higher temperature because more energy is needed to overcome that intermolecular force. If you look at water here has hydrogen bonding. Ethanol also has hydrogen bonding. Look at where they are. Carbon disulfide is non-polar, and it has the lowest. But it gets a little trickier in the middle here because there's kind of more going on that we're going to talk about in one moment. Look at this graph. What trends do you see in this graph? So first, look at these molecules. If you look at a periodic table here, right, these are all, like here's carbon, silicon, germanium, tin. That would be like carbon, silicon, germanium, tin. So each one of these colors is a different group or vertical column on the periodic table. And the trend that you should see is that generally, as the molecular weight goes up, the boiling point goes up, right? Generally, as the molecular weight goes up, the boiling point goes up. That's the general trend. But you notice these three outliers. These guys do not follow that trend. We would expect them to have very low boiling points, but something else is going on. Can you see what else is going on? What's going on is that these guys can undergo hydrogen bonding, right? Here's our F and O. So what trend do you see in this graph? That hydrogen bonding makes boiling points larger, right? Come on. Because more energy. Is needed to overcome. Sorry, that's not the neatest handwriting there. But then you need to look at, well, why does it generally increase? Right? We can see this is sort of the hydrogen bonding is how you get these anomalies, but generally the higher the molecular weight equals higher boiling points. And so why is that? That's one question that we still haven't answered. And here's the answer. The higher the mass of the molecule, the more electrons it has. Therefore, it is more polarizable, has the strongest London dispersion forces, and a higher melting point or boiling point. That's a very big deal. So why is it that SNH4 has a much higher boiling point than CH4? It's because it is more massive, and because it's more massive, it has more electrons. That makes the London dispersion forces, just the London dispersion forces, much stronger than the London dispersion forces in these other molecules. This is looking at this table right here and this chart. These are great places where you might see some when you are assessed in this when you are assessed on this in a few weeks, you might need to write a CER, claim evidence reasoning. This is always asking you, right, to explain why. If I asked you, explain why carbon disulfide has a much smaller boiling point than water, could you explain that based on this? Right? There's some really interesting things on this graph, or on this table, I should say, as well. Chloroform does not have hydrogen bonding, but it is polar. Its molar mass is a lot more than methanol. Methanol can have hydrogen bonding. So that has still a little bit higher boiling point. Carbon tetrachloride, look at this guy here. He is non-polar. Why is his boiling point so high? His boiling point is almost the same as ethanol, which can hydrogen bond, because carbon tetrachloride has a large mass. It has lots and lots and lots of electrons. So it has lots of electrons, and it's got relatively strong London dispersion forces, because as we said, the higher the mass, the more electrons, stronger London dispersion forces, more energy it takes to overcome them. So you may want to reference this page when you're trying to write those claim evidence reasonings in a few weeks. Okay? We have just a couple more questions about liquids. So when we talk about a fluid, just so we can keep our vocabulary correct here, what is a fluid? A fluid is anything that flows. And what is that? It's a word that we use to describe both gases and liquids. So a kind of term that encompasses both of those is a fluid. I just need to get that vocabulary word out there. So we are going to start talking about what happens when you go from one phase to another phase. And that is, if you go from liquid to a gas, that's called vaporization. So vaporization is when you go from a liquid to a gas or vapor? That was a question way back, literally like chapter 1. A vapor is just the word that we use to talk about the gas phase of a substance that isn't a gas at room temperature. Like water vapor. We don't say water gas, we say water vapor because water is a liquid at room temperature. We don't say oxygen vapor, we say oxygen gas because oxygen is a gas at room temperature. So that's an umbrella term for any time you're going from a liquid to a gas. But you can break that down into 2 different terms, evaporation and boiling. And we may use these terms interchangeably in life, but in science, they mean 2 different things. Evaporation is when you go from that liquid to a gas, but only at the surface of the of the liquid. And it has to be below the boiling point. It has to be below the boiling point. Evaporation is what happens when you just leave a glass of water out for a few days. You will notice that the level of the water after a few days will get lower and lower and lower. Even though the water never gets anywhere near the boiling point of water. Why is that? Because the particles of gas on the particles of liquid on the surface become a gas. How can that be? We'll look at that in a moment. When you reach the boiling point, then even a water molecule down here at the bottom will have enough energy to become a gas. And that's what the bubbles are. When you see bubbles forming in boiling water, those are bubbles of water vapor. And there are lots of molecules that have enough energy to overcome the attractive forces between the water molecules and become a gas. So how does evaporation occur? How can water evaporate even though it's well below the boiling point? Well, we look back at this graph. We saw this graph in our last video, right? The blue line is a lower temperature. At that lower temperature, look, only this small amount, the blue area, represents the number of molecules that have enough energy to evaporate. So even if just at room temperature, some molecules, even though the average temperature is much lower, or the average kinetic energy of the water molecules is much lower, some of them will always have enough energy to evaporate. And then this red line, at a higher temperature, many more molecules have enough energy to evaporate. So more water evaporates at a higher temperature. That's how like a dryer works or your hair dryer works, right? It gives the molecules enough energy or more energy so that they can evaporate, and it evaporates quicker because those molecules are higher. Okay, your hair does not become, right, 100 degrees Celsius. That would burn you if you may have burned your hair or your scalp using like a flat iron. But if you just use a regular hair dryer, yeah, your hair gets hot, but it does not get 100 degrees Celsius. This, we're just going to go into a little bit more about what's really going on at the surface of a liquid. So at the surface of a liquid, we said no matter what temperature, some molecules have enough energy to overcome the attractive forces and become a gas. Because they are becoming a gas, there is a pressure involved, and we call that pressure vapor pressure. It's a measure of the force exerted by a gas above a liquid. Right, the measure of the force exerted by a gas above a liquid. So no matter what temperature water or liquid you have, there is some vapor pressure, right? This is showing the compound ethanol at 0 degrees Celsius, very cold. These molecules don't have a lot of energy, but some of them do have enough energy to become a gas. This is an instrument called a manometer, and this is measuring the vapor pressure of that ethanol, and you can see it's 12.2 millimeters of mercury. If I increase the temperature of the ethanol to 20 degrees Celsius, I give those molecules more energy, and now more molecules have enough energy to overcome the attractive forces holding the ethanol together. More of them are able to become a gas, and you can see the vapor pressure increases. And this graph down here shows vapor pressures on the y-axis, and as the temperature increases, what happens to the vapor pressure? This is the trend that you would see. So as the temperature increases, vapor pressure also increases. So the blue line here is water. At 0 degrees Celsius, it's a solid. Vapor pressure is very little, almost zero. As you increase the temperature, the vapor pressure increases. More molecules have enough energy to overcome the hydrogen bonding. And then look at what happens at 100 degrees Celsius. What does the vapor pressure equal? 760. Where have you seen that number before? Right? That number right there is that number right there is standard air pressure. This is atmospheric air pressure. And that leads us to what really is boiling point, right? Boiling point is not the temperature at which a liquid boils. I know, that seems kind of weird. It is the temperature where the vapor pressure is equal to the atmospheric pressure. The temperature where the vapor pressure of the liquid is equal to the atmospheric pressure. Right? So look at this picture right here. This is, we're at sea level, right? At sea level, we're at 101.3 kPa. So this is standard atmospheric pressure. At 70 degrees Celsius, is the water boiling? No, we are well below the boiling point of water. I have to raise the temperature of the water to 100 degrees Celsius. Now, there is boiling because vapor pressure is equal to atmospheric pressure. But now look what happens when I change the atmospheric pressure. This might be something, you would have to be very high up. I don't think it actually gets anywhere near this low on top of Mount Everest, but it gets pretty low on top of Mount Everest. And look at what happens now. Is this water boiling? Yes. Why? Because the vapor pressure is equal to the atmospheric pressure. Because the atmospheric pressure is so much lower. At higher altitudes, water boils at a much lower temperature. That is why you will often see the different baking directions on baked goods if you live at higher altitudes, because the boiling point of water is much lower there. If you were to cook the cake in the oven for the same amount of time, you would burn your cake, you would dry out your cake because the water is going to evaporate way sooner at a lower atmospheric pressure. So what is 100 degrees Celsius? We talk about 100 degrees Celsius as the boiling point of water. And I just told you that that's really not true. Sometimes the boiling point of water is 100 degrees Celsius. Sometimes the boiling point of water is as low as 70 degrees Celsius. So what is 100 degrees Celsius? That's what we would call the normal boiling point. That's the boiling point at 1 atm. So that's what we generally refer to as the boiling point of water. You can see it if I go back to this table, right? It clarifies. This is the normal boiling point of several substances. when you guys I may have talked about this in class, but I took a bunch of students on a trip to Peru with me way back in 2004. Yeah, back in 2004. And we would, eat and drink. We would cook our own food. We made some macaroni and cheese one night, and the water that we used was water literally from a stream. So in order to cook our food, we needed to boil the water first. Now, we had pure water that we had chemically purified for the first 3 or 4 pots of macaroni and cheese. The last pot of macaroni and cheese, we didn't have time to purify it, but we thought, we'll just boil the water. Boiling the water will kill off any bacteria. We should be fine. So the last group that ate macaroni and cheese made from that unpurified water. That water had only been boiled. And those people, you guys may know, if you cook out, who are the last people to eat? Well, they're the cooks, right? Because they have to keep cooking. So the 3 people who were the cooks that night got some of the worst food poisoning that I've ever seen, because when they boiled the water and they thought they were killing off all the bacteria weren't really dead, because the temperature, the boiling point of the water then, I wish I had taken a picture or had a thermometer, but it was much less than 100 degrees Celsius. I think I looked up our altitude and it was only about 92 degrees Celsius. So we boiled the water. We thought we were killing off all the bacteria. We didn't, and we gave ourselves some food poisoning. So that's a real life example, or a few real life examples of this phenomenon here. Another example of this is how you can go the other way. And a pressure cooker works at increasing the atmospheric pressure and therefore increasing the boiling point of water. Okay, there's lots of cool videos that I will put up on Schoology that explain this if you want a little bit more, context of it. The homework tonight is numbers 14 through 21. Again, there's not a lot of, there's no calculations. It's really all about explaining and multiple choice. All of these that we have talked about are good places where you could see a potential CER. Why is the boiling point of water so much lower on Mount Everest? Right? Why is it, right? I could ask you why for this trend. Why is it that when you increase the temperature, you increase the vapor pressure? Right? So the answer to that would be basically this graph. So there's a lot to think about here. And tonight, do questions 14 through 21. Check your work, and we'll continue talking about liquids in the next video.